Imagine computers that never overheat, chips that waste zero energy, and data centers that run with perfect efficiency. Sounds like science fiction, right? But today that fiction is closer to reality. Scientists have just achieved something once thought impossible, turning germanium, a key material in electronics, into a superconductor. This breakthrough could shatter the limits of current technology, opening the door to zero-resistance electronics. For decades we've battled heat and energy loss in our devices. Now, the rules of computing may be about to change. The era of perfectly efficient chips might finally be within reach. Germanium, the unsung hero of electronics, has always played second fiddle to silicon, but a team at Delft University, using standard chip-making techniques, made ultra-pure germanium films and tested them at extremely low temperatures. To their shock, the resistance didn't just drop, it vanished. Germanium became a superconductor. What's revolutionary is how they did it, with the same tools already used in the semiconductor industry. No exotic materials, no special processes. Just the familiar methods perfected over decades. This means superconducting devices could be mass-produced, using the infrastructure we already have. The door to industrial-scale superconducting electronics is now wide open. Superconductivity is when a material's electrical resistance drops to zero at very low temperatures. Normally, electrons bump into atoms, losing energy as heat, but in a superconductor, electrons pair up and flow without friction. This means a current could, in theory, flow forever, with no power source, as long as it stays cold. For computer chips, this is a game changer. No resistance means no heat, faster speeds, and almost no wasted energy. Signals could travel across chips without degrading, enabling more powerful designs. Until now, superconductors were exotic and impractical for mass production. But with germanium, we might finally bring this superpower to everyday electronics. With superconducting germanium, we can build Josephson junctions, the quantum switches at the heart of superconducting circuits. These junctions are essential for quantum computers, acting as the quantum version of transistors. Previously, making them was slow and painstaking, limiting the scale of quantum hardware. Now, thanks to wafer-scale germanium, we can print millions of Josephson junctions using standard chip manufacturing. This transforms quantum hardware from a lab craft into an industrial process. Complex quantum circuits can be mass-produced, just like today's processors. The quantum future just got a lot more scalable. The real magic? Germanium can be both a semiconductor and a superconductor on the same chip. By tweaking the manufacturing process, we can create regions for traditional transistors and others for superconducting circuits, all on one wafer. This integration solves a huge problem in quantum computing: the messy, inefficient wiring between cold quantum chips and warm classical controllers. With both types of circuits side by side, control logic and qubits can communicate directly, reducing noise and boosting efficiency. This could finally make large-scale, fault-tolerant quantum computers possible. The architecture becomes simpler, faster, and easier to scale. It's like putting the surgeon's hands directly where they're needed. No more clumsy mittens. The path to practical quantum computing just got a lot clearer. Superconducting germanium isn't just for quantum computers. Its sensitivity enables next-generation sensors, like ultra-precise detectors for astronomy, able to spot the faintest signals from distant galaxies. Earth-monitoring satellites could use these chips to track subtle magnetic changes, helping predict earthquakes or monitor water resources. In medicine, smaller, more sensitive brain scanners could become affordable and widespread, revolutionizing diagnosis and research. And in data centers, superconducting interconnects could slash energy use and heat, shrinking the carbon footprint of our digital world. The impact stretches from deep space to the human brain, and everywhere in between. While a superconducting laptop is still far off, the biggest gains will come where energy use is highest. This technology could redefine what's possible in science, medicine, and computing. This is just the beginning. The biggest challenge? Temperature. Superconductivity in germanium only appears near absolute zero. Keeping chips that cold is expensive and impractical for everyday devices, though it's standard in quantum labs. Scaling up production is another hurdle, making flawless, ultra-pure wafers at industrial scale won't be easy. Integrating semiconductor and superconductor regions on a single chip is a complex engineering puzzle. but the roadmap is clearer than ever. The first applications will be in quantum computing and advanced sensors. As the technology matures, and if scientists can raise the superconducting temperature, the possibilities will explode. This isn't just a new material, it's a new vision for the future of electronics. The next era of computing is waiting. What will we build with it?